My name is Udovičić, and today I'll talk to you about a tool for executable code complexity visualization. So the growth of the automotive industry puts increasing demands on software developed for modern vehicles. The architecture of such software is developed in a modular fashion and can be very large. Usually one main module contains other modules further composed of other smaller modules. The number of levels in such form can be very large, and the code review process in this case can be very complicated and time-consuming, as well as code debugging. The complexity of the software solution is sometimes unnecessarily large, and reducing its size can be beneficial in terms of development and maintenance of time and cost. A visual representation of the code, most often a graph or diagram, allows the developer to review code features more easily and thus spot and correct any potential errors. So why visual representation? Because it enables efficient analysis of the program code architecture, and because you can see the whole structure of code in only one picture, it contributes to time and money savings, and also increases the quality and productivity of programmers because it's easier to spot potential and existing errors as responses, and it makes it easier to manage code complexity in terms of reducing it. So my proposed tool for visualization is based on the analysis of specific interfaces and modules within the software. It's basically a data flow graph between software modules, and as a result of analysis, a graphical representation of the entire software architecture, along with the graph navigation with mouse clicks between the levels, is presented to users. And it will be explained in more detail in the next slides. So the first step, and one of the most important, is collecting software solution documentation. Software solution documentation can be written in many different formats and by using different tools. It is important to define the way that the documentation has to be written and standardize it, because documentation is the starting point of the code complexity analysis within the tool. The proposed tool defines the documentation in a standardized nested JSON format, since the tool heavily relies on the internet technologies like JavaScript and the subsequent steps of the analysis and structure display. Objects in JSON files, they always contain a pair of values, a key and a value. The key must always be a string, while the value can be a number, string, or object in an array. If the value of an object is another object, then such structure is called nested. And we use the nested data structures in this tool because it allows the display of parent and offspring nodes. The upper node represents the root node, and it has no parent node. All other nodes have exactly one. In this tool, architecture like this one is used. The host is a central program to which all its subordinate programs are connected. Services are programs organized into groups that run within different instances on a parent host. A component is a software module that can be reused and combined with other components. Each component has several units that use interfaces to communicate with external units. Interfaces can be provided and required. The provided interfaces are interfaces implemented in a unit, and required interfaces are those that are necessary for a unit to function properly and are implemented within another unit. Generated files are extracting data from them. It's a second step in creation, and because most software solutions in the automotive industry are written in C programming language, this code was also written in C programming language. The GCC compiler creates the required map file, and the generated map file, it consists of several parts, such as input sections, memory configuration data, a linker script, and a memory map. And the data needed for reconstruction of the program code architecture in this tool can be found in the connection script and memory card section. The script that implements the extraction of data from the map file was created in Python programming language using the pandas library. So the graphical user interface is the most important part, and it is created in JavaScript language using the D3 library, the user interface is divided into several parts, which are created as separate HTML pages. They are interacted by buttons, interconnected by buttons. At first, an interface selection window is shown, which allows the user to select the desired view via the host or the service using two buttons. The user can return to the home page at any time. On the next slide, we can see the graphical interface. At the top, we can choose different views. On the left, we see the graph created from documentation. And on the right is the graph created from data from generated files, meaning the actual code. At the bottom, there is a button that displays a comparative graph that is showing the differences between the left and the right graph. It is called the comparison graph, and the data from documentation is saved in the first list, and the data from the generated files in the second list. These lists now contain the names of all program modules and interfaces that are in the documentation. The algorithm essentially goes through the lists and tries to determine whether the elements of the first list are in the second, or whether all the names of program interfaces and modules from the documentation are in the generated files. The found values are saved in the new list. The new list may contain duplicate values, and it must be filtered to avoid duplication. On this side, we can see the comparison graph, and below the graph, a tabular report is shown. The report shows the total number of interfaces, the number of correctly implemented interfaces, and the number of incorrectly implemented interfaces, meaning the number of missing interfaces. The graphical interface for displaying a comparative graph shows only one graph. Hereby, the possible differences between the two previous graphs are highlighted using the appropriate colors and icons. On the next slide, we can see the three possible situations that may happen when we use this tool. So the first one shows a situation when all documented interfaces are implemented and there is no errors. So all icons are green. The second one shows a warning when an interface name is misspelled, and it shows a yellow icon and a warning that interface name is misspelled. And the third one shows an error when interface is missing. So these two interfaces that have red icons are missing from either documentation or code. In conclusion, to sum it up, we discovered that hierarchical display and navigation through graph nodes allow the user to analyze the complexity of the code, and the comparative graph provides insight into potential errors such as misspelled interface names in the program code or their deviation from the name in the documentation, and insight into missing interfaces or interfaces that are not implemented in the software solution. Thank you for your attention and sorry for the inconvenience. If you have any questions,